So in general, small oscillation and simple harmonic are the synonyms to each other. So the best example of small oscillation is all about the spring mass system. And you can also just formulate the thing such that any other oscillatory system can be behave like a simple harmonic motion. So first we will discuss what is simple harmonic motion in one dimension, and then we will go for more than one dimension. So whenever my force is restoring in nature, and that will be something like this. So force is restoring, that is minus sign is there, and it's linear in x. Then the motion, and it is obviously it should be bounded in nature. It should be bounded. Then what will happen? We have a simple harmonic motion. What will happen to simple harmonic motion? For the simple harmonic motion, basically the frequency omega is constant, and which will be k upon m. So yes, you can easily solve all this thing. You can solve here that f is equal to nothing but m d square x upon dt square plus kx is equal to 0. And this equation is d square x upon dt square plus k upon m, x is equal to 0. And this famous constant omega square is identified as what? K upon m. And you can find the omega for the oscillatory system. This is very trivial and very simple. But any oscillatory system, even if you have, suppose I have something where force is not linear, then obviously your omega is not constant. We can see this thing into different lectures. Okay. But today we are going to focus ourselves mainly on the part where force is linear in nature. So what is force? The force is nothing. We are talking about conservative force. So force F can be defined as minus del V upon del X. So if F is linear, then what should be nature of V? If F is linear, तो V का nature कैसा होगा?
Linear only.
Then I'm talking about V. The del V upon del X is linear. Then what is your V?
Of kx square type.
Obviously, the V will be something like parabolic. So Vx is something like parabolic in nature. So your Vx is equal to proportional to x square. So this is your parabolic. So if we have linear force or parabolic potential with the positive sign in potential, so why the negative sign will come into force such that it will be restoring in nature. So whenever you can approximate any potential, suppose you have something, this kind of potential is there. And what you can do, you can just try to approximate this kind of potential with some parabolic potential. Then what you can do, you can treat it as a small oscillation. And here the most important point is that about which point it is going to do the small oscillation. So obviously it should just do the small oscillation about point x is equal to x naught. And this x naught is identified as what? Equilibrium point. And this x naught is not only equilibrium, that should be identified as what? Stable equilibrium point. So what is a stable equilibrium point? Obviously, suppose if you have this kind of potential, suppose I have this kind of potential, and if we have this x is equal to x naught, what will happen to x is equal to x naught? This is minima of a curve. So we have del v upon del x must be equal to 0. So this is minima of a curve. So del V upon del X must be equal to 0. At which point at X is equal to X naught, as well as the second order derivative del square V upon del X square must be greater than 0. So why it will be minima at X is equal to X naught. Then it is identified as a stable equilibrium point. And whenever you have a stable equilibrium point, you can, if you are just displacing the particle from this particular equilibrium point, there is some restoring force such that you can compare it with the spring mass system. So in a spring mass system, what will happen? Suppose you are at the equilibrium point, either you are going to extend it or you are going to compress it. The force is always towards the equilibrium point, and this force is try to bring back at the equilibrium position. So if you have this sort of information such that you have equilibrium point, you can easily calculate the omega of you can easily calculate the angular frequency. So for one dimension, we can easily approximate if particle is doing some oscillatory motion. Oscillatory motion means the motion is about equilibrium point, and obviously it is bounded in nature. So if particle is going to have some oscillatory motion, then what will happen? We can approximate that potential up to a simple harmonic, or we can approximate the potential up to harmonic level by assuming that displacement is very small. So this is the fundamental of your basically small oscillation. I think we have done it also into this very rigorously into the stability analysis, isn't it? But I am just going to recall this because we have done it earlier. So just I am going to recall the theory, and then we will go for more than one generalized coordinate, and how we will use the Lagrangian to formulate the small oscillation. We will try to go for this. Are you getting my point? यहाँ तक clear है?
Yes, sir.
Okay. So suppose I have any potential Vx, and I can do the Taylor expansion of this particular Vx. So what will be Taylor expansion of this Vx? At about which point? About x is equal to x naught. And what is this x naught? Stable equilibrium point. So this is my potential. So suppose this kind of situation is there. So what you have Vx naught plus del V upon del x at x is equal to x naught, and that value is x minus x naught plus 1 by 2 del square V upon del x square at x is equal to x naught, and this value is x minus x naught whole square, and all other term which is order of x minus x naught to the power cube term is there. So we can have this potential. So one potential will be something like constant part, linear part, harmonic part, and cubic part, and quadratic part. And you can just take this and make it sum. You will get this particular Vx. Sorry, this particular Vx. But what is beautiful part? Sorry, what is beautiful part about the small oscillation is that we can neglect the unharmonic potential. We can neglect the unharmonic part of the potential. Are you getting my point? Unharmonic, by assuming what is the cause and what is the logic behind this particular negligence of this particular higher term, by assuming that x minus x naught tends to, and cubic term tends to 0, because it is very small. So this is logic. This is very this is very small. and you can just neglect into this particular Taylor expansion. By the way, what will be happen to del V upon del X?
It will be 0.
Is equal to 0. Why? Because it is a stable equilibrium point. So this will be directly 0. And what will happen to this one? Obviously, some positive value, isn't it? Because it is a stable equilibrium point. So you have x is equal to x naught is a stable equilibrium point. So Vx is equal to Vx naught plus half del square V upon del x square x minus x naught. And what I can do, I can write some V naught plus half k x minus x naught whole square. And this V naught is constant. It will just tell you all about the reference point. Okay. So for the, and obviously if constant potential is there, it will be added to the potential or subtracted to the potential. Nothing to do with the force, because constant potential have effect of zero force. So we can assume for our convenience, we can assume this will be 0. So what I can do, I can just approximate my potential as half k x minus x naught whole square. We can approximate it, and what is going to happen? And the force F is basically minus del V upon del X, and that is nothing but minus k x minus x naught. And now look at, this is linear in nature. And if it is linear, then you can get omega is nothing but k upon m, and which will be del square V upon del x square, at which point x is equal to x naught by m. So this value is your omega, and this is angular frequency for the small oscillation. And omega is one of the very fundamental parameter for a small oscillation. So you can use it for different type of problem. But now, today we are just going to discuss what will happen when we have more than one equilibrium point and more than one generalized coordinate. Then what will be this particular k? This k. That is very interesting. But before going to this, just go for one particular problem such that you can recall all the theory of this particular small oscillation in one dimension, and then we will go for basically 2-dimension or more than 1-dimension part, and we will use the Lagrangian and all the concept. Okay? यहाँ तक clear है ना?
Yes, sir.
Yes.
Sir, why we neglected V naught? Please repeat once.
Because it is constant, and it will not help you to if the force is constant, if potential is constant, if you are just going to take the derivative, what will happen to this one? 0. So there is not any role of constant potential into force.
Okay, sir.
So let's go for one basic problem. So suppose Vx is equal to x square by 2 minus x cube by 3. And particle of mass m is equal to 1 unit. It's just doing the small oscillation about stable equilibrium point. Obviously, if it will do small oscillation, that should be a stable equilibrium point. Then what you have to do? First, you have to find the what will be angular frequency. So what will be angular frequency? So we have to just calculate. Omega is nothing but del square V upon del x square at x is equal to x naught by m, and m is equal to 1 unit. So what you have to do? You have to calculate you have to find what will be x naught. This is the most important thing. है ना? ये हमें find करना पड़ेगा. So what will happen? Del V upon del x is equal to 0. So x minus x square is equal to 0. So x is equal to 0 and 1. So these 2 points are the equilibrium point, but we have to figure it out which one is stable equilibrium point. So for the stable equilibrium point, we have to just go for del square V upon del x square, and that value is minus 1 minus 2x. So for x is equal to 0 and x is equal to 1, which one is a stable equilibrium point? 0 or 1?
0.
0. How do you know? So you have to just go for del square V upon del x square at x is equal to 0. You will get 1, which is greater than 0. So x is equal to 0 is basically stable equilibrium point. X is equal to 0 क्या है आपका? Stable equilibrium point. Okay. Clear है ये? Okay. Now you can also check what will happen to x is equal to 1. So del square V upon del x square is equal to 1 minus 2 into 1, and this is at x is equal to 1, and this value is equal to what? Minus 1, which is less than 0. So x is equal to 1 is what? Unstable equilibrium point. Isn't it?
Yes,
That
sir.
is unstable equilibrium point. So, and if you will put x is equal to 1, that value is what? 1 by 6. So this is very famous potential. If you can go and you can plot it. So this will be something like this. So now you can check x is equal to 0 is a stable equilibrium point. And if your energy is in this particular, and if your energy is such that your particle will be into this particular valley, you can do oscillatory motion, but that oscillatory motion can be approximated to the small oscillation. And that should be, and this will be not allowed. This should be allowed. So what will be your omega? Your omega is equal to root under del square V upon del x square. X is equal to 0 or 1. क्या होगा?
0.
0.
0.
X is equal to 0 and m value is also 0. So what will be answer?
1.
1. So omega is equal to what? 1 unit. So omega is equal to 1 unit with the angular frequency for a small oscillation. Please mind it. If you are going to approximate it with the parabolic potential. What is parabolic potential? You have this kind of shape. Okay. So if you can approximate your potential for the parabolic potential, and now you can see, you can easily approximate it up to, if you are going for this level, if you are neglecting the higher level, then obviously you can approximate this thing with the parabola. And whenever you have parabolic potential and you have a stable equilibrium point, what you have? You have a small oscillation. So this is not a part of this thing just for making thing, just you have to revise from the stability analysis. Okay. So if some people have done a stability analysis, they can start from here. But those people who have done a stability analysis, they can recall all the theory we have done into that part, isn't it? So let's go for a theory behind the small oscillation. Okay? The general theory of a small oscillation. By the way, Lagrangian for the harmonic oscillator is given by what? Half m x dot square minus half k x square. This is kinetic energy and this is potential energy. So you can see for the oscillatory motion for the small oscillation. And this is the one of the system where you have always a small oscillation or always simple harmonic motion. Are you getting my point? Always. So this, now you can see, if system is just behaving like simple harmonic motion, the kinetic energy have dimension of x dot square and potential energy have dimension of x square. Are you people happy?
Yes, sir.
ठीक है ना? So kinetic energy T is proportional to x dot square and V is proportional to what? x square. Something like this. Then if you have this kind of situation, then you can analyze the system with the small oscillation or simple harmonic motion. And you can equate your all system to one spring mass system. For this particular potential, what will be spring constant here? क्या होगा spring constant? अगर मैं इसको
So delta 2v by del x square.
Exactly. So your k is nothing, but that value is del square v upon del x square at x is equal to 0. And this value is 1. So equivalent spring constant is 1. But what is a spring constant? Is that just a number? Yes, it is a number in one dimension. But exactly, you will see this is not a number. This is some kind of arrangement. This is some kind of matrix representation for the more degree of freedom. So let's go for a general theory of small oscillation. यहाँ तक clear है?
Yes, sir.
I have just deliberately revised the thing because I think some people were new who are not attend all this class earlier. So we will do it later, but we can use it into next 1 or 2 chapter. Okay. So today we are just going to finish we are just going to finish the theory behind the small oscillation. Okay. And we are just talking about in a general sense. So what is this particular general sense? So you have potential, and now your potential V is a function of generalized coordinate Q1, Q2, Q3 up to Qn. And the ith generalized coordinate is identified as Qi0. So this is your, Qi is the ith generalized coordinate. So if you have this much of generalized coordinate, we can assume that Q10, Q20, Qi0, Qn0 are the stable equilibrium point. What are these? Stable equilibrium point. Are you getting my point? So what is the theory behind the small oscillation? What is the theory behind the small oscillation? You have to do the Taylor expansion for potential about which point?
Stable equilibrium.
Stable equilibrium point. Up to which level? Up to which order?
Second order.
Second order. So this is the thing we have to just go for it. So we have my potential, and this potential can be approximated. So you can just go and compare it with 2-dimension or 3-dimension also. What will be next term? Anyone? So this is your first term. Okay. What will be next term? The linear term?
Yes.
So that will be del V upon del Qi, and we can take the summation over I. At which point? Qi is equal to?
Qi0.
Qi0, and linear term is, I have not, Qi minus Qi0. Okay. Up to that, everyone is comfortable?
Yes, sir.
Okay. Now, let's go for our next term. So in a next term, what we have to do? We have to give double summation or single summation?
Double summation.
Double summation. Why? because we have to go for I and J. What will happen? Del square V upon del Qi del Qj about which point? Qi is equal to Qi0 and Qj is equal to Qj0. Yes?
Yes, sir.
And what about this one? This is nothing. Qi minus Qi0 and you have Qj minus Qj0. Now look at here. This is you. Suppose you have two generalized coordinate. How many term will be there here? Suppose you have two generalized coordinate. How many term will be there?
Two terms.
Two term. Okay, good. Q1, Q2. If you have two generalized coordinate, how many term will be there?
4
3.
Three term.
Oh, sorry, sir. 4.
terms.
Four term. Okay.
Yes, sir.
What will be that term? Q1, Q1. First you will differentiate with respect to Q1. Again you will differentiate with respect to Q1. This is your first term.
Yes, sir.
Second term is what?
Q1,
Q1, Q2.
Q1, Q2.
Third term is what?
Q2,
Q2, Q1. Fourth term is what? Q2, Q2.
Q2, Q2.
Now you can represent this whole particular formulation as a form of matrix. Represent कर सकते हैं ना? इसको पूरे को आप एक मैट्रिक्स के थ्रू रिप्रेजेंट कर सकते हो, है ना?
Yes, sir.
So suppose you have two coordinates, then that matrix will be, what will be dimension of that matrix?
2
2
cross 2.
cross 2.
2 cross 2, exactly. And we are just going for the higher order term. So higher order term is the cubical term, we can neglect it. So obviously it is stable, it is equilibrium point. So what will be happen to this one? 0. Okay. This one, this term must be what? 0. And now look at what will be my potential. And what now it's look little bit more clumsy. So what we are going to do, we will just going to translate each and every coordinate with certain amount. Look at, we are just doing some extra work here. Can I write Qi minus Qi0 is equal to eta I? लिख सकते हैं ना?
Yes, sir.
So if Qi is equal to Qi0, then eta I will be 0. Yes or no?
Sir.
लिख सकते हैं. Similarly, Qj minus Qj0 is equal to what? Eta j. So we can translate each and every point such that our equilibrium point will be always 0, 0, 0, 0, 0. You can do it. है ना? Scaling कर सकते हैं. You are just doing this thing as scaling. And the beautiful part is that dqi is equivalent to d eta I. Yes. So, and this part will be something like my potential can be written as, if we are translating all about which point, eta I and eta j, then this will be something like 0, 0. Plus this will be summation over I del square V del eta I del eta j eta I eta j, and higher order term we are neglecting. And we can assume this value is a reference point, and we can assume for our simplicity that this value is equal to 0, as we have assumed in our one dimension case. So, and half is also there. Sorry, half will be also there, na? Half will be also there. Last में half किया था कि नहीं? Last जब टेलर expansion किया था तो?
हाँ, sir.
Yes, sir.
Okay, good. So half will be also there. Factorial 2 is actually, nahi?
Yes, sir.
Okay. Now you can see your potential energy is written as half summation over del square V del eta j, eta I and eta j. This is eta I, eta j or in a matrix form, we can write half VI J eta I eta J. लिख सकते हैं इसे? And now you can see your harmonic for harmonic oscillator. What is your potential? Half K x square, and you can write something like half K x into x. लिख सकते हो ना? And same thing we have written here also. Don't worry. The potential is proportional to x to eta square, dimension of displacement square. This is displacement from the equilibrium point, isn't it?
Yes, sir.
This is displacement from the equilibrium point. So you can easily have. Now, if you have this as your potential energy, and with the analogy of first 1 degree of freedom of harmonic oscillator, what should be my kinetic energy? If it is potential energy, then what should be my kinetic energy?
The half
Half
eta I dot square.
half. Obviously, you have eta I dot, eta j dot, and that value is Tij. Isn't it? And what should be Tij? With the analogy of this one. What is Vij? What is Vij? Del square V, del eta I, del eta j. This is your Vij term. So what will be your Tij term? With the analogy. बताइए.
Del square T upon
Very good. Del square T upon.
dou of
Del eta I dot.
I
Very
AT.
good. Del eta I dot, del eta j dot from the symmetry. Yes? है ना? Why we can use it? Look at from the logic. In the logic, what will be your total energy? The total energy is kinetic energy plus potential energy for the harmonic oscillator. Yes or no?
Yes, sir.
Yes. If I will put m is equal to 1 and k is equal to 1, I can write half x dot square plus half x square. So you can see there are perfect symmetry for kinetic energy as well as potential energy. जैसा kinetic energy का नेचर बढ़ेगा जाएगा वैसा ही potential energy का भी नेचर कुछ उस तरह से होगा. Such that your energy should be constant. Means अगर potential energy बढ़ता जा रहा है ऐसे तो kinetic energy ऐसे करके क्या होगा? घटता जाएगा. Isn't it? तभी तो total energy constant मिलेगी.
Yes, sir.
So what you have? You can formulate your kinetic energy matrix on the basis of knowing what will be nature of your potential energy matrix. Everyone is comfortable up to this level?
सर यहाँ TIJ VIJ मैट्रिक्स है क्या?
Matrix element. This is matrix element actually.
एलिमेंट okay.
This is matrix element. Okay? यहां तक क्लियर है? Yes or no? Okay. So should I remove this thing?
Yes, sir.
Okay. So basically, we have V is equal to half Vij eta I eta j, and T is equal to half Tij eta I dot eta j dot. Clear है ना? So we can write the Lagrangian. लिख सकते हैं? So just we are writing the Lagrangian of a system, and that value is half Tij eta I dot eta j dot minus half Vij eta I eta j. Yes? Can I write something like this?
Yes, sir.
Okay. And now we can go for a equation of motion. So if we are going for the equation of motion, then what will happen? And suppose we are doing equation of motion for jth coordinate, then this will be equation of motion. Clear है ये? Yes या no?
Yes, sir.
So,
Yes, sir.
जरा इसे कैलकुलेट करके बताओ तो jth के लिए कैलकुलेट कर रहे हैं, हमें बचेगा क्या? jth डॉट के लिए गया तो क्या बचा? eta I डॉट. So can I write this thing? Tij eta I double dot plus Vij eta I must be equal to 0.
Yes, sir.
देखो कर सकते हैं क्या? अब ऐसे ऐसे कितने इक्वेशन मिलेंगे आपको?
4.
4. क्यों?
I test.
n number of equation, जितने number of generalized coordinate होंगे, है ना?
Yes, sir.
And so you have n number of equation, so you have to solve them simultaneously, है ना? आप जब उसे simultaneously solve करोगे, then obviously you can get the answer. Now, by the way, which type of solution you can have for this eta I? किस तरह का solution होता है?
Harmonic oscillated.
Obviously, किस तरह का solution होगा? Mathematically, you have eta I is equal to some constant, let's say Ci. Ai is the direction, e to the power I omega t. ऐसा solution होगा?
Yes, sir.
है ना?
Yes, sir.
Anything, किसी भी डिफरेंशियल इक्वेशन का अगर इस तरह का नेचर है तो उसके सॉल्यूशन ये होंगे. Now, if you are going to put it this thing into this particular equation, then what you will get? Tij Ci Ai minus omega square e to the power I omega t plus Vij Ci Ai e to the power I omega t is equal to 0. So which term we can get the common? We can get common Ci Ai e to the power I omega t, and we have Vij minus omega square Tij must be equal to 0. ठीक है ना?
Yes, sir.
And this cannot be 0 because if this will be 0, that should be the trivial solution. हमें कैसा solution चाहिए? Non-trivial solution. So for the non-trivial solution, we have Vij, determinant of Vij minus omega square Tij must be equal to 0. And now how many equations you have to solve something like that? N number of equation. And if you are going to solve this n number of equation, so that can be represented as a form of matrix, isn't it?
Yes, sir.
And what will be that matrix? That matrix can be written as something T matrix minus omega square V must be equal to 0. So this thing, this is for the individual I and j, and finally you can just go for the all proper matrix. So you have n cross n matrix here. They are actually a square matrix, and you will be surprised that potential energy and kinetic energy both will be symmetric matrix. This is very interesting. And you can have something like eigenvalue type equation, है ना? And this
Yes,
is
sir.
nothing but a determinant. Okay, this is nothing but determinant, and this is identified as secular equation. इसे आप क्या कहते हो? Secular equation. Now, what will happen when you will? Now, how many omega you will get from here? N number of omega, because it is n cross n matrix. So you have n number of omega, and now you can get the yes.
Sir, in the generalized equation, why the position of potential and kinetic energy are interchange? Means here V minus omega square Tij is equal to 0. And when we generalize it now, it becomes T minus.
अरे यार, जीरो होने से क्या होगा? इसको इधर लिख दो तो क्या होगा? माइनस को प्लस कर दे, कोई प्रॉब्लम होगा क्या? दिस नेगेटिव साइन इज ऑलवेज देयर ना. सॉरी यहाँ पर ओह सॉरी मैंने गलती लिख दी है. सॉरी v minus omega square t. Sorry. Okay, this is correct. Not this is correct. Sorry. V minus omega square t. Okay. So V is basically, extremely sorry. V is potential energy matrix. T is kinetic energy. The theory is little bit tough, but when you will try to go for the solving the problem, it is very easy, very straightforward. Don't worry. Okay? So just try to sink this thing into yourself, because sometime you have to solve the problem with first principle. I will give you one problem that came into last year in JEST exam that can be only solved with the first principle. Okay. Anyway, so let's try to go for a next one. यहाँ तक clear है ना?
Yes, sir.
Sorry, again, please check it. V minus omega square t. Okay. Now, the solution of secular equation, the value of omega, I am just starting from here. The value of omega which will satisfy the secular equation value of omega which will satisfy the secular equation known as normal frequency if omega is greater than 0. Omega is equal to 0 is not any frequency. Omega is greater than 0. Omega is less than 0 has not any physical significance. So omega must be greater than 0. So this is known as normal frequency. The lowest value of omega is identified as fundamental frequency. Next higher level is known as first overtone. Okay. Next higher level is first overtone. What will be second higher level? What will be second higher level? Batao?
One higher to this.
Huh? What is name of that?
Second overtone.
Second overtone. Okay. So fundamental is the first, then first overtone, then second overtone. As in a quantum mechanics, ground state is the first, then first excited state, then second excited state. Okay. The formulation of that quantum mechanics also very, very much resemblance with this particular theory. Now, if omega I is equal to omega j, if omega I is equal to omega j, they are known as degenerate frequency. If omega I is equal to not omega j, they are known as non-degenerate frequency. Okay, they are known as what? Non-degenerate frequency. Up to that, everyone is comfortable?
Yes, sir.
Okay. Now we will just talk about normal modes. For given value of omega and omega is equal to, let's say, omega I, if any column vector xi satisfy the relation and what is the relation? V minus omega square t xi must be equal to 0. Then xi is normal mode corresponds to normal frequency omega is equal to omega I. So if you have, and you can find normal modes for omega is equal to 0 also, because it will just tell you all about the direction. Okay, what is the nature of motion? And this will tell you just which kind of amount, which kind of frequency is associated to that independent motion. And in general, यहाँ तक clear है ना? We will solve each and everything. Don't worry. एक प्रॉब्लम लेके एक एक चीज इसे करने की कोशिश करेंगे, ठीक है?
Yes, sir.
In general, we choose normal modes must be linearly independent. Okay. So in general, we will choose normal mode is what? Linearly independent. But what we will do? We will just find the orthogonal normal mode. What will be beauty of that orthogonal normal mode? If it is orthogonal, it will be always linearly independent. All orthogonal vector is linearly independent, isn't it?
Yes, sir.
Because it will just create a basis that any motion of that particular system can be represented by the linear combination of all normal modes. And last but not the least, the normalization constant, the normalization condition is given by xi transpose T matrix xi must be equal to 1. So this is your normalization condition such that you can use it as a something kind of unit vector, and you will just incorporate the effect of mass into the direction. So why we have taken this kinetic energy here, and that will be give you the normalization, the weight factor actually for the basically what will be your modes and what will be your direction. Okay, so these are the theory.
Sir, T kinetic energy matrix.
T is the kinetic energy, exactly. T is kinetic energy matrix. T is kinetic energy matrix. Okay, so this is the basic theory behind the small oscillation. I deliberately discuss it from one dimension, such that if you people have forget the one dimension thing, or some people have joined from the Lagrangian, then they can also inherently take this particular thing. So in the next class, we will just try to solve the problem. I will solve the problem with the first principle. Each and everything we will discuss, and then I will tell you how to solve the problem with in a shortcut method for the examination purpose. Okay?
Yes, sir.
So tomorrow we will solve different types of problem related to normal frequency. So in general, आपके exam में normal frequency पूछा जाता है. Sometime they can ask you normal modes also. So you have to prepare for each and everything. Okay? The best part, and I have just take all this discussion from Goldstein. Okay?
Yes, sir.
Okay. Thank you. If
Thank
you
you,
have
sir.
any doubt, you can just
Thank you, sir.
raise your question.